Hello, finally. Okay. So yeah, I can confirm. I'm able to stream now. Let's go. So this will be the 5th episode of GCP Cloud Fundamentals Core Infrastructure. So let's go. I will share with you my browser. Let's sign in and continue from where we left last time. Okay, so let's have a look here. About 7 hours remaining. To get in the next league, I need 300 points. I think I can do it. Like, yeah, 300 will be enough. Okay, so let's do this 300 points. Okay, well, the whole course is 400 points, so maybe I will not be really able to do that, but some course.
In this section of the course, we'll explore container.
So we already had the sections about storage, virtual machine networks, resources, hierarchy of resources, access to resources. Then let's go.
And help you understand how they are used. In this section of the course, we'll explore containers and help you understand how they are used. Infrastructure as a Service, or IaaS, allows you to share compute resources with other developers by using virtual machines to virtualize the hardware.
Okay, so this was one of the first concepts we touched at the beginning of this course. IaaS, then PaaS, and SaaS.
This lets each developer deploy their own operating system, OS, access the hardware, and build their applications in a self-contained environment without.
This lets each developer deploy their own operating system, access the hardware, and build their application in a self-contained environment with access to RAM, file system, networking interfaces. So, okay. Virtualizing the hardware. The rest is managed.
Access to RAM, file systems, networking interfaces, etc. This is where containers come in. The idea of a container is to give the independent scalability of workloads in PaaS and an abstraction layer of the OS and hardware in IaaS. A configurable system. The idea of a container is to give the independent scalability of workloads in PaaS and an abstraction layer of the OS and hardware in IaaS. A configurable system lets you install your favorite runtime, web server, database, or middleware, configure the underlying system resources, such as disk space, disk I/O, or networking, and build as you like. But flexibility comes with a cost. The smallest unit of compute is an app with its VM. The guest OS might be large, even gigabytes in size, and take minutes to boot. As demand for your application increases, you have to copy an entire VM and boot the guest OS for each instance of your app, which can be slow and costly.
Okay, so when we arrive to standardizing our operations, if we need to scale up or to augment our computation volumes instead of just running a cluster, if we have VMs, we need to augment the number of VMs, which implies that we need to ask for more infrastructure as a services. Therefore, it can be slow and costly, okay.
A container is an invisible box around your code and its dependencies, with limited access to its own partition of the file system and hardware. It only requires a few system calls to create, and it starts as quickly as a process. All that's needed on each host is an OS kernel that supports containers and a container runtime. In essence, the OS is being virtualized. It scales like PaaS, but gives you nearly the same flexibility as IaaS.
Okay, it scales like PaaS, but gives you nearly the same flexibility as IaaS. Okay, so the containers are, I will say in this statement, I see that containers are kind of a parallel solution, an alternative solution to PaaS, platform as a service, because platform as a service means that your virtualization is managed, so you don't need to actually manage your virtualized resources. Therefore, you just need to launch on them your software. Instead, when you use containers, you achieve something similar, but you still need to manage your containers. Okay, this maybe is the difference.
This makes code ultra-portable, and the OS and hardware can be treated as a black box. So you can go from development to staging to production, or from your laptop to the cloud, without changing or rebuilding anything. As an example, let's say you want to scale a web server. With a container, you can do this in seconds and deploy dozens or hundreds of them, depending on the size of your workload, on a single host. That's just a simple example of scaling one container, running the whole application on a single host. However, you'll probably want to build your applications using lots of containers, each performing their own function like microservices. If you build them this way and connect them with network connections, you can make them modular, deploy easily, and scale independently across a group of hosts. The hosts can scale up and down and start and stop containers as demand for your app changes or as hosts fail.
Okay. Next activity. There are some nuances which I'm
A product that helps
not
manage
sure 100%. I will need to revise the differences between IaaS, PaaS, containerized environment. They all work sometimes in parallel, sometimes together, and they may, they have really little differences, which make a huge impact when deciding your architecture and your strategy.
manage and scale containerized applications is Kubernetes. So to save time and effort when scaling applications and workloads, Kubernetes can be bootstrapped using Google Kubernetes Engine, GKE. So what is Kubernetes? Kubernetes is an open source platform for managing containerized workloads and services. It makes it easy to orchestrate many containers on many hosts, scale them as microservices, and easily deploy rollouts and rollbacks. At the highest
Services make it easy to orchestrate many containers on many hosts, scale them as microservices, and deploy rollouts and rollbacks. It's a set of APIs to deploy containers on a set of nodes called a cluster.
level, Kubernetes is a set of APIs that you can use to deploy containers on a set of nodes called a cluster. The system is divided into a set of primary components that run as the control plane and a set of nodes that run containers. In Kubernetes, a node represents a computing instance, like a machine. Note that this is different to a node on Google Cloud, which is a virtual machine running in Compute Engine. You can describe a set of applications and how they should interact with each other, and Kubernetes determines how to make that happen. Deploying containers on nodes by using a wrapper around one or more containers is what defines a pod. A pod is
Deploying containers on nodes by using a wrapper around one or more containers is what defines a pod. So a pod is a wrapper around one or more container running on a node. A pod is the smallest unit in Kubernetes that you can create or deploy.
the smallest unit in Kubernetes that you can create or deploy. It represents a running process on your cluster as either a component of your application
It represents on your cluster as either a component of your application or an entire app.
or an entire app. Generally, you only have one container per pod. But if you have multiple containers with a hard dependency, you can package them into a single pod and share networking and storage resources between them. The pod provides a unique network IP and set of ports for your containers and configurable options that govern how your container should run. One way to run a container in a pod in Kubernetes is to use the kubectl run command, which starts a deployment with a container running inside a pod. A deployment represents a group of replicas of the same pod and keeps your pods running even when the node.
A deployment represents a group of replicas of the same pod and keeps your pods running even when the nodes they run on fail.
They run on fail. A deployment could represent a component of an application or even an entire app. To see a list of the running pods in your project, run the command kubectl get pods. Kubernetes creates a service with a fixed IP address for your pods, and a controller says, I need to...
So the first command was kubectl run command. She started deployment of container running inside a pod. Okay, then we have kubectl get pods. Kubernetes create a service with a fixed IP address for your pods, and controller says, I need to attach an external load balancer with a public IP address to that service so others outside the cluster can access it.
Attach an external load balancer with a public IP address to that service so others outside the cluster can access it. In GKE, the load balancer is created as a network load balancer.
Is a network load balancer. Okay, so it acts at the level of network load balancer because they work with fixed IPs.
Any client that reaches that IP address will be routed to a pod behind the service.
That IP address. Any client that reaches that IP address. Will be routed to a pod behind the service.
A service is an abstraction which defines a logical set of pods and a policy by which to access them. As deployments create and destroy pods, pods will be assigned their own IP addresses, but those addresses don't remain stable over time. A service group is a set of pods and provides a stable endpoint or fixed IP address for them. For example, if you create two sets of pods called front-end and back-end and put them behind their own services, the back-end pods might change, but front-end pods are not aware of this. They simply refer to the back-end service. To scale a deployment, run the kubectl scale command. In this example, 3 pods are created in your deployment, and they're placed behind the service and share one fixed IP address. You could also use auto-scaling with other kinds of parameters. For example, you can specify that the number of pods should increase when CPU utilization reaches a certain limit. So far, we've seen how to run imperative commands like expose and scale. This works well to learn and test Kubernetes step by step. But the real strength of Kubernetes comes when you work in a declarative way. Instead of issuing commands, you provide a configuration file that tells Kubernetes what you want your desired state to look like, and Kubernetes determines how to do it. You accomplish this by using a deployment config file. You can check your deployment to make sure the proper number of replicas is running by using either kubectl get deployments or kubectl describe deployments. To run 5 replicas instead of 3, all you do is update the deployment config file and run the kubectl apply command to use the updated config file. You can still reach your endpoint as before by using kubectl get services to get the external IP of the service and reach the public IP address from a client. The last question is, what happens when you want to update a new version of your app? Well, you want to update your container to get new code in front of users, but rolling out all those changes at one time would be risky. So in this case, you would use kubectl rollout, or change your deployment configuration file, and then apply the change using kubectl apply. New pods will then be created according to your new update strategy. Here's an example configuration that will create new version pods individually and wait for a new pod to be available before destroying one of the old pods.
Okay, we have a lot.
So now that we have a basic understanding of containers and Kubernetes, let's talk about Google Kubernetes Engine, or GKE. GKE is a Google-hosted managed Kubernetes service in the cloud. The GKE environment consists of multiple machines, specifically compute engine instances, grouped together to form a cluster. You can create a Kubernetes cluster with Kubernetes Engine, but how is GKE different from Kubernetes?
Group together to form a cluster. You can create a Kubernetes cluster with Kubernetes Engine, but how is GKE different from...
From the user's perspective, it's a lot simpler. GKE manages all the control plane components for us. It still exposes an IP address to which we send all of our Kubernetes API requests, but GKE is responsible for provisioning and managing all the control plane infrastructure behind it. It also eliminates the need for a separate control plane. Node configuration and management depends on the type of GKE mode you use. With the autopilot mode, which is recommended, GKE manages the underlying infrastructure such as node configuration, auto-scaling, auto-upgrades, baseline security configurations, and baseline networking configuration. With the standard mode, you manage the underlying infrastructure, including configuring the individual nodes. Let's examine the benefits and functionality of autopilot in more detail. Autopilot is optimized for production. Autopilot helps produce a strong security posture, and autopilot also promotes operational efficiency. The GKE standard mode has the same functionality as autopilot, but you're responsible for the configuration, management, and optimization of the cluster. Unless you require the specific level of configuration control offered by GKE standard, it's recommended that you use autopilot mode. You can create a Kubernetes cluster with Kubernetes Engine by using the Google Cloud Console or the gcloud command that's provided by the Cloud Software Development Kit. GKE clusters can be customized, and they support different machine types, number of nodes, and network settings. Kubernetes provides the mechanisms through which you interact with your cluster. Kubernetes commands and resources are used to deploy and manage applications, perform administration tasks, set policies, and monitor the health of deployed workloads. Running a GKE cluster comes with the benefit of advanced cluster management features that Google Cloud provides. These include Google Cloud's load balancing for compute engine instances, node pools to designate subsets of nodes within a cluster for additional flexibility, automatic scaling of your cluster's node instance count, automatic upgrades for your cluster's node software, node auto repair to maintain node health and availability, and logging and monitoring with Google Cloud Observability for visibility into your cluster. To start up Kubernetes on a cluster in GKE, all you do is run this command: gcloud container clusters create k1.
Okay, so I will say that this is a brief introduction. We don't have a lab in this case. Maybe we will have a lab after, or maybe in another course. What is a Kubernetes pod? A group of containers. Where do the resources used to build Cloud Kubernetes Engine clusters come from? Compute engine. Okay, next. Great.
So far in this course, we provided an introduction to Google Cloud and explored the options and benefits related to using virtual machines, networks, storage, and containers in the cloud. In the final section of the course, we'll turn our attention to developing applications in the cloud. We'll begin with Cloud Run, which is a managed compute platform that runs stateless containers via web requests or pub sub events. Cloud Run is serverless.
That run stateless containers via web requests or pub sub events.
That means it removes all infrastructure management tasks so you can focus on developing applications. It's built on Knative, an open API and runtime environment built on Kubernetes.
Knative.
It can be fully managed on Google Cloud, on Google Kubernetes Engine, or anywhere Knative runs. Cloud Run is fast. It can automatically scale up and down from zero almost instantaneously, and it charges only for the resources used, calculated down to the nearest 100 milliseconds, so you'll never pay for over-provisioned resources. The Cloud Run developer workflow is a straightforward three-step process. First, you write your application using your favorite programming language. This application should start a server that listens for web requests.
Okay. So start a server that listens for web requests. It's a lot and nothing. Second, you build and package your application to container image. Okay. And third, the container image is pushed to artifact registry where Cloud Run will deploy it. Once you've deployed your container image, you'll get unique HTTPS rollback.
Second, you build and package your application into a container image. And third, the container image is pushed to artifact registry where Cloud Run will deploy it. Once you've deployed your container image, you'll get a unique HTTPS URL back. Cloud Run then starts your container on demand to handle requests and ensures that all incoming requests are handled by dynamically adding and removing containers. Because Cloud Run is serverless, it means that you as a developer can focus on building your application and not on building and maintaining the infrastructure that powers it.
Okay.
Some use cases, a container-based workflow is great because it gives you a great amount of transparency and flexibility. Sometimes you're just looking for a way to turn source code into an HTTPS endpoint, and you want your vendor to make sure your container image is secure, well-configured, and built in a consistent way. With Cloud Run, you can do both. You can use a container-based workflow as well as a source-based workflow. The source-based approach will deploy source code instead of a container image. Cloud Run then builds the source and packages the application into a container image. Cloud Run does this using BuildPacks, an open-source project. Cloud Run handles HTTPS serving for you. That means you only have to worry about handling web requests, and you can let Cloud Run take care of adding the encryption. The pricing model on Cloud Run is unique, as you only pay for the system resources you use while a container is handling web requests, with a granularity of 100 milliseconds, and when it's starting or shutting down. You don't pay for anything if your container doesn't handle requests. Additionally, there's a small fee for every 1 million requests you serve. The price of container time increases with CPU and memory. A container with more vCPU and memory is more expensive. You can use Cloud Run to run any binary as long as it's compiled for Linux 64-bit. Now, this means you can use Cloud Run to run web applications written using popular languages, such as Java, Python, Node.js, PHP, Go, and C++. You can also run code written in less popular languages, such as COBOL, Haskell, and Perl. As long as your app handles web requests, you're good to go.
Let's go. Next activity.
Many applications contain event-driven parts. For example, an application that lets users upload images. When that event takes place, the image might need to be processed in a few different ways, like converting the image to a standard format, converting a thumbnail into different sizes, and storing each new file in a repository. This function could be integrated into the application, but then you'd have to provide compute resources for it, whether it happens once a millisecond or once a day. With Cloud Run functions, you write a single-purpose function that completes the necessary image manipulations and then arrange for it to automatically run whenever a new image is uploaded. Cloud Run functions is a lightweight, event-based asynchronous compute solution that allows you to create small, single-purpose functions that respond to cloud events, without the need to manage a server or a runtime environment. These functions can be used to construct application workflows from individual business logic tasks. Cloud Run functions can also connect and extend cloud services. You're billed to the nearest 100 milliseconds, but only while your code is running. Cloud Run Function supports writing source code in a number of programming languages. These include Node.js, Python, Go, Java, .NET Core, Ruby, and PHP. For more information about the supported specific versions, refer to the runtime's documentation. Events from Cloud Storage and PubSub can trigger Cloud Run functions asynchronously, or you can use HTTP invocation for synchronous execution.
Okay, so Cloud Storage and PubSub can trigger Cloud Run functions asynchronously, or you can use HTTP invocation for synchronous execution. It's a lot, nothing. I need to apply these concepts. Otherwise, they will be just some ideas. So, hello, Cloud Run, this lab, blah, blah, blah. Cloud Run is a managed compute platform that enables you to run stateless containers that are invocable via HTTP requests. Cloud Run is serverless. It abstracts away all infrastructure management so you can focus on what matters the most, building great applications. Cloud Run is built from Knative, letting you choose to run your containers either fully managed with Cloud Run or in your JKE clusters with Cloud Run on JKE. The goal of this lab is for you to build a simple containerized application image and deploy it to Cloud Run. Objectives. In these labs, you learn to enable the Cloud Run API. Wow. Create a simple Node.js application that can be deployed as a serverless, stateless container. Containerize your application. Okay, so serverless, stateless container. Then we containerize it and upload to artifact registry. Deploy a containerized application on Cloud Run. Delete unneeded images to avoid incurring extra storage charges. Let's go start lab. Let's open this in incognito. So I'm logging in the platform. Okay, I understand. Let's go. So now I will need to choose this. Okay, we have it. So yeah, I'm Spain. I agree. Agree and continue. Let's go. So the instructions are: first, task 1, enable the Cloud Run API and configure your shell environment. From Cloud Shell, enable the Cloud Run API. So normally we enabled the APIs from here. This time we will do it from the Cloud Shell. It's just an alternative. Okay, so when you want to enable an API from the shell, you just need to type gcloud services enable and the name of the API. I mean, this will be the package. I'm not sure how it's called, this format. Yeah, run googleapis.com. Run is the name, the node of one of the Google APIs, the one we want to activate. If you are asked to authorize, okay, set the compute region. So when we use the Cloud Shell, we can configure with set commands elements like compute region. We may put East 1, US East 1, yes. What? Yeah, the lab is not asking us for any specific region, so I will just use US East 1 as indicated here. And then create a location environment variable. So in the commands, we will not need to use the name of the region. We will just need to use $location. Task 2, write the sample application. So in Cloud Shell, in this task, you will build a simple Express-based Node.js application which responds to HTTP requests. Node.js Express is web application framework, minimalist web application framework. Yeah, who wants can search more about it. So we will create a directory called hello world and we will enter it. We are in hello world now. So next you'll be creating and editing files. To edit files, use Nano or the Cloud Shell code editor by clicking on Open Editor. So there's the possibility to have a visual editor here. I prefer Nano. Create a package.json file, then add the following content to it. So Nano package.json. Okay, so we will have this JSON file describing the service we're going to run. Okay. That's it. So we'll just need to, yes. Okay. Next, in the same directory, create an index.js file and copy the following lines into it. So nano index.js, then in this index, we put 3 constants. Okay, the library, the entry point, which is a function called express, port, and then app get and app listen. Okay. You can use many other languages to get started with Cloud Run. You can find instruction for other languages, blah, blah, blah. So task 3, containerize your app and upload it to Artifact Registry. So now we will create a Docker file, and inside, using the Docker file structure, we will write a Docker Node.js image from the hub Docker, create and change to the app directory. So one of the first instructions when executing the container will be to start from user src app, copy application dependency manifest to the container image. Okay, so we will basically copy this package JSON file we just created. Okay, then after we create a copy of this file in the container, we install the production dependencies. Okay. Okay, now build your container image using cloud build by running the following command from the directory containing the Docker file. Note that the Google Cloud project inherent variable in command which contains your lab project ID. So, okay, we will build and put it in this path in the artifact registry. So gcloud builds submit tag, okay, and executing from the same location as the Docker file, it will assume that those are the instructions. Okay. Okay. Cloud build is a service that executes your build on Google Cloud. It executes a series of build steps where each build step is run in a Docker container to produce your application container. And push it to artifact only one command. Once pushed to the registry, you will see a success message containing the image name. The image is stored in artifact registry and can be reused if desired. List all the container images associated with your current project using this command. Okay, status success. We can see it from Google Cloud Container Images. Okay, gcloud out configure Docker. You may be prompted, do you want to continue? To run and test the application locally from Cloud Shell, start using this standard Docker command. Okay. So Docker run and they give the port where I can contact it and the image which I want to paste this run. In the Cloud Shell window, click on Web Preview and select Preview on port 8080. No, wait. This will open a browser. You can also simply use curl localhost. Okay, so it's working. Okay, now we can deploy it to Cloud Run. Deploying your containerized application to Cloud Run is done using the following command, adding your project ID. So you just run, deploy the image, other tags about location authorization. Service name, hello world, enter. You may be prompted, okay, wait a few moments until the deployment is complete. On success, the command line displays the service URL. You can now visit your deploy container by opening the... You have just deployed an application package in a container image to Cloud Run. Cloud Run automatically horizontally scales your container image to handle the received requests, then scales down when demand decreases. In your own environment, you only pay for the CPU, memory, and networking consumed during request handling. For this lab, you use gcloud command line. Cloud Run is also available via Cloud Console. From navigation, blah, blah, blah. Okay. I will go to Cloud Run here. So you can see I have my container. So it's being deployed. Then we will just gcloud container images, delete. Okay, when prompted to continue, blah, 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 to delete the clone, use this command. Okay. Come on. Okay, let's see. Hello world. Yay. We have our hello world. Big as a house. Let's go. Then we did it. Now we will clean. We will delete the image. Please. Now we will delete the service, the Cloud Run service. I'm prompting to type yes. Okay, deleted. End your lab. 10 minutes earlier. Clean. Submit. Okay, so we finished this lab. Now we can continue to the next activity. Which of these statements about Cloud Run functions are correct? can be used to extend cloud services. Is integrated with cloud logging. I'm not sure about that. Oh shit, I kicked the camera. It's always at least one time per session. Okay, so why might a Google Cloud customer choose to use Cloud Run functions? Maybe the second. Select the managed compute platform that lets you run stateless containers through web request pub/sub events. Cloud Run. Yeah. Let's see. Man, I did all wrong. So this is good. This was good. So it's scalable function as a service and extends Google Cloud services. Okay, so maybe it's the first. And then what? Oh, okay, so here I'm missing. To get credit from it, you must select all the correct options. So maybe this one. Retake. So, okay. Okay, so wow, okay, submit. Oh, 100%, nice. Next.
Generative AI and large language models are
Let's see one thing. Okay, this section looks really fast. And then we have the course summary. So we will finish the course today. Nice.
proving to be powerful tools, but to leverage their capabilities,
here we have a crossover with generative AI and large language models, which are proving to be powerful tools, but to leverage their capabilities, it's important to understand
their architecture. It's also important to consider best practices when implementing these technologies. The goal of this module, titled Google Cloud Prompt Engineering Guide, is to help with these important steps. In this guide to prompt engineering, you'll get answers to the questions: what is generative AI? What is a large language model? What is prompt engineering? You'll also explore prompt engineering best practices. Before we delve into this lesson, let's define the interchangeably used terms such as generative AI and large language models, or LLMs. While both terms describe AI models capable of generating human-like responses based on input prompts in many references, it's important to note that they are not identical. Generative AI encompasses a broader range of models capable of generating various types of content beyond just text, while LLM specifically refers to a subset of generative AI models focusing on language tasks. We'll thoroughly explore each term in this lesson. So, let's begin with an important question. What is generative AI? Generative artificial intelligence, which is commonly referred to as Gen AI, is a subset of artificial intelligence that is capable of creating text, images, and other data using generative models, often in response to prompts. It has grown in popularity hugely since 2021, but artificial intelligence has been around since the mid-1950s. By the way, a prompt is a specific instruction, question, or cue given to a computer program or user to initiate a specific action or response, but we'll examine this more later. In its current format, Gen AI models are like conversational programs that can generate content based on the inputs supplied. Gen AI models learn the patterns and structure from the input training data and then create new data with similar characteristics. Generative AI has uses across a wide range of industries, including software development, healthcare, finance, entertainment, customer service, and sales. However, rather than exploring all generative AI applications, this training will specifically focus on articulating prompts to harness the power of Gen AI effectively. Let me introduce a scenario that we'll make reference to throughout this section of the training. We've included it to help put some of this theory into practice. Meet Sasha, cloud architect who needs to create a prototype design of a Google Cloud VPC network architecture for Simple Bank. Sasha wants to save time by combining her existing knowledge of cloud architecture and generative AI tools to create a usable prototype design. Sasha was excited to learn about Gemini, Google's Gen AI tool, since having the tool inside the Google Cloud console means that she can access it without any additional installs. We'll check back in with Sasha later. Let's spend some time exploring large language models, which are highly sophisticated computer programs trained on gigantic amounts of data that can be in the text or image format. But how are they trained? And why do they need training at all?
Large language models refer to large general-purpose language models that can be pre-trained and then fine-tuned for specific purposes. In this context, large refers to the size of the training dataset, which can sometimes be in the petabyte scale, and the number of parameters. Parameters are the memories and knowledge that the machine has learned during the model training. They determine the ability of the model to solve a problem, such as predicting text, and can reach billions, even trillions in size. General purpose means that the models can sufficiently solve common problems. This is thanks to the commonality of a human language, regardless of the specific tasks. Saying LLMs are pre-trained and fine-tuned means that they have been pre-trained for a general purpose with a large dataset, and then fine-tuned for specific goals with a much smaller dataset. But how are LLMs trained? When you submit a prompt to an LLM, it calculates the probability of the correct answer from its pre-trained model. The probability is determined through a task called pre-training. Pre-training an LLM involves feeding a massive dataset of text, images, and code to the model so that it can learn the underlying structure and patterns of the language. This process helps the model understand and generate human language more effectively. In this way, the LLM works like a fancy autocomplete, suggesting the most common correct response to the prompt. But sometimes the LLM gives a completely wrong answer. This is called a hallucination. Hallucinations are words or phrases that are generated by the model that are often nonsensical or grammatically incorrect. This happens because LLMs can only understand the information they were trained on. This means that they might not be aware of your business's proprietary or domain-specific data. Also, they do not have access to real-time information. To make matters worse, LLMs only understand the information that is explicitly given to them in the prompt. In other words, they often assume that the prompt is true. Ultimately, an LLM does not know anything outside what it is trained on, and cannot truly know if the information is accurate. But what causes a hallucination? Hallucinations can be caused by a number of factors, including the model is not trained on enough data, the model is trained on noisy or dirty data, the model is not given enough context, or the model is not given enough constraints. Hallucinations can be a problem for LLMs because they can make the output text difficult to understand. They can also make the model more likely to generate incorrect or misleading information. But we will see in the prompt engineering section that there are things we can do to minimize this problem. Okay, but knowing where the sun is will not help Sasha with her current task. Luckily for Sasha, Google Cloud offers a generative AI model called Gemini, which can act as an always-on collaborator. This Gen AI-powered assistant can help a wide range of Google Cloud users, including developers, data scientists, and operators. To provide an integrated assistance experience, Gemini is embedded into many Google Cloud products. Gemini has access to a massive range of data, including Google Cloud documentation, tutorials, and samples. With the right prompts, it can produce detailed suggestions and guides on what resources best suit Sasha's current challenge and their configuration. Gemini can even create detailed G-Cloud commands and insert them into Cloud Shell for her. She just needs to articulate her needs in a way that gets the best response from Gemini. For example, if she uses the prompt, "How can I create a network that uses IPv4 and IPv6 addresses?" she will get a response that details how to do just that. You've learned that a large language model is a huge object model containing a massive dataset of text. But how can you extract the information you need from this dataset? This is where prompt engineering comes in. A prompt is the text you feed to the model, and prompt engineering is a way of articulating your prompts to get the best response from the model. Prompts can be in the form of a question, and are categorized into 4 categories: zero-shot, one-shot, few-shot, and role prompts. Zero-shot prompts do not contain any context or examples to assist the model. For example, here, the prompt, "What is the capital of France?" does not provide any examples on what a capital is. Clearly, for this example, that's not too important. But for more specific and technical prompts, an example would help refine the scope of the response from Gemini. One-shot prompts, however, provide one example to the model for context. Here we ask for the capital of France again, but we provide Italy and Rome as our example. And few-shot prompts provide at least 2 examples to the model for context. Here, our prompt is updated to also include Japan and Tokyo in our examples. And then there are role prompts, which provide a frame of reference for the model to work from as it answers our questions. In our example, we state, "I want you to act as a business professor. I'll give you a term, and you will correctly explain its meaning. Make sure your answers are always right. What is ROI?" For Sasha's needs, using role prompts might be the best solution. She can define what is required and in what context. This means the LLM will have a clear point of reference when supplying an answer. Now that you've seen the types of prompts you can create, let's explore the 2 elements of a prompt, the preamble and the input. The preamble refers to the introductory text you provide to give the model context and instructions before your main question or request. Think of it as setting the stage for the LLM to better understand what you want. It can include the context for the task itself, and some examples to guide the model. The input is the central request you're making to the LLM. It is what the instruction or task will act upon. In our example, the input is, "Comment. I don't know what to think about this video." The review is, based on the preamble, which includes context and some examples, Gemini reviews the input and suggests if the review is positive, neutral, or negative. It's worth noting that not all the components are required for a prompt, and the format can change depending on the task at hand. The element order can also change. Let's amend Sasha's original prompt. "How can I create a network that uses IPv4 and IPv6 addresses?" and add a role context to the input fed into Gemini. She also adds the detail of needing a dual stack subnet. The new prompt is, I want you to act as a cloud architect in Google Cloud. How can I use G-Cloud to create a network that uses IPv4 and IPv6 subnets? But since Gemini maintains its own interaction context, she could have just asked, I want you to act as a cloud architect in Google Cloud. How can I adjust the G-Cloud command provided to create a subnet to ensure the subnet is a dual stack? Now that you've had a chance to explore what GenAI is, what large language models are and how they're trained, and what prompt engineering is, it's time to explore some prompt engineering best practices. The first best practice is to write detailed and explicit instructions. The more vague the prompt, the more chance the model will produce a result that is not usable. Be clear and concise in the prompts that you feed into the model. Next, be sure to define boundaries for the prompt. It's better to instruct the model on what to do rather than what not to do. If the model gets stuck, give a few fallback outputs that work in various situations. For example, something like, I'm still learning about that, to use when unsure. Another best practice is to adopt a persona for your input. Adding a persona for the model can provide meaningful context to help it focus on related questions, which can help improve accuracy. This prompt would help Sasha, the cloud architect, get started with prototyping a network architecture for Symbol Bank. And finally, it's best practice to keep each sentence concise. Longer sentences can sometimes produce suboptimal results. It's best to break long sentences in a prompt into a series of shorter sentences and simpler tasks. So, let's return to Sasha and use what we've learned so far. Sasha updates her prompt to, you're a cloud architect. You want to build a Google Cloud VPC network that can be centrally managed. You also connect to other VPC networks in your company's other regions. You don't want to have many different sets of firewall policies to maintain. What sort of network architecture would you recommend? With this new prompt, Gemini proposes a hub-and-spoke network architecture recommendation, which fits Sasha's needs exactly. By refining and amending her prompts, Sasha has articulated her requirements in a way that Gemini can respond with the correct focus and level of detail.
Okay, let's go. Next activity. So we're reaching the end of this course. Which of the following is not a good practice for constructing prompts? Is not a good practice. Include long and detailed sentences. Give short and simple. Vary your prompts. What does this mean? It depends. How can you avoid hallucinations when using a large language model? Generative AI is a type of artificial intelligence that can. Which one of the following is not a type of prompt? Oh man. Real prompt engineering best practice lesson. Fuck you, man. I mean, keep it short and simple. If I need something like the capital of Paris, why should I? Fuck. Vary your prompts. Include long and detailed sentences. Avoid ambiguity. Include a long and detailed sentence. Maybe this one. It's not a type of prompt. Too short. Hallucinations. Train the model on a clean created data set. And then generate text images, other data. That's it. Oh, I won the lottery. Okay. Next.
Congratulations on completing the Google Cloud Fundamentals Core Infrastructure Training course. Before you go, let's take a few minutes to review what we've covered. In Module 1, you were introduced to Google Cloud and cloud computing. Specifically, you explored the concept of managed infrastructure and managed services through IaaS, Infrastructure as a Service, and PaaS, Platform as a Service, the Google Cloud Network, Google Cloud's focus on security throughout our infrastructure, how Google publishes key elements of technology using open source licenses, and Google Cloud's pricing structure and billing tools. In Module 2, you learned about the Google Cloud resource hierarchy, which is made up of 4 levels: resources, projects, folders, and an organization node. You also learned about defining policies and their downward inheritance, when to use Cloud Identity and Access Management, or Cloud IAM, and the 4 ways to access and interact with Google Cloud, through the Cloud Console, the Cloud SDK and Cloud Shell, APIs, and the Google Cloud App. In Module 3, you explored how Compute Engine works, with a focus on virtual machines and virtual networking. You were introduced to the VPC, or Virtual Private Cloud, Compute Engine's auto-scaling feature, and important Google Virtual Private Cloud compatibility features like routing tables, firewalls, VPC peering, and shared VPC, all of which result in the need for less network management. He also explored cloud load balancing, a fully distributed, connected, and Firestore. He also examined the 4 storage classes that make up cloud storage: standard storage, data, visible boxes around your code and its dependencies. Kubernetes, Google-hosted managed Kubernetes. 6. The focus was on developing applications in the cloud that let you run stateless container sub-events. Asynchronous compute solution to. Finally, in Module 7, you explored how to combine answers to the following question. What is prompting by identifying? We hope that this course is just the beginning of your Google Cloud journey. For more training and hands-on practice, explore the different learning paths training. To form businesses with Google Cloud technology, you might consider working toward a Google Cloud certification. Certifications. Thanks for completing this course. We'll see you next time.
Great. So, Cloud Fundamentals, core infrastructure. Okay, we have this nice PDF. What are these links? Resource and access in the cloud. Let's see. Oh, look here. I will download all of them. So we'll download all of them in this new folder, 03. Fundamentals or infrastructure. Let's save it here. Okay. I'm not sure, but maybe the course will, the exam will change this year. I will still need to check this. Meanwhile, I think the best thing I can do is just to study, continue studying. Oh, I have this badge. Great. Course survey. I mean, okay. Somehow satisfied. I mean, very satisfied. They did the best they could do. Thank you for feedback. Next. Let's go.
Hello, I'm Philip Meyer.
So they've already directed me to the next course. I will go to my learning path homepage. So as we can see now, I have the first, second, and third course already completed. Now in the next 6 hours, maybe I will be promoted to the Gold League. For sure, I will be not drop down to the Bronze League. I hope these people here does not make surprises. So for now I will close, and well, I will continue with the rest of the learning path with the 4th course on the cloud fundamentals, and see you in the